Welcome everyone to this new video tutorial on the usage of GIS, and in this tutorial we will concentrate on the issue of watershed delineation and also processing of DEMs, especially of the SRTM data, which is something like worldwide available topographic data. So these are rasters which contains the height of the surface. Therefore, I've downloaded already a new file from landcover.org. You can just visit that. You don't need any kind of permission or registering or some kind of account. And I've downloaded a file that is located, or the scene is located in central Mongolia, where I've done a lot of work. And this is a file. For SRTM data, there are several processing steps available. So there's something like a raw data file, and then they have done, or the USGS I think has done some processing of that file. I've downloaded filled finished B. That means that some pixels where no information was available have been already filled by the processing. And this is revision number B. I'm not really sure what every step contains, so I will now just import that data in my GIS project, and as you can see, or no, as you cannot see, there's nothing in it. It's just a gray file, but that depends on your scene. And as you can see here, the lowest possible value in that scene is minus 32,000 something, and the highest 32,767. No, yeah, that's correct. And why is it like that? So the SRTM data, or the height information of a pixel, will range something from minus 442, I think, is in the Dead Sea, up to 8,000, nearly 9,000 meters in the Himalaya region. So what integer type will fit that information? If you will choose 8-bit, 0 up to 255, not enough. Strictly not enough. So you can switch to 9-bit. It's quite uncommon. So what is next step? 16-bit. And here we have it. So it's a 60-bit signed integer, which will give you a value ranging from minus 32,000 up to plus 32,000. So first of all, I would like to show you how to increase the visibility of this layer. So just right click, go to properties of that file, and you can see here a tab called symbology. And first of all, you can easily adjust the range by choosing from custom settings below and say, well, I think we can start at 1,000 and we will go up to 4,000. Let's say okay first. So let's have a look. More contrast available. And if you also adjust the color ramp, so the grayish tones are there, they sucks, especially for topographic data. You should choose a more common format like this green to brown color range, which will give you a lot more information than the other layer, or the other color range. So we will choose that. Well, first of all, it's like that. So the lower areas are visible in this brown, and the higher areas are visible in that green. We have to invert that color ramp to get a better look on our scene. So now the lower areas, like here in the floodplains, are marked in green, or that greenish blue or something like that, and the highest values appear in the mountainous region in the southwestern part of that scene, which is the path number 134 and row number 27. If you would like to download the same file, are marked here in that brownish colors. And so we will go a little bit more into detail with that file, because I would like to show you some special things in that. So let's have a look on that tiny spot here. This is a place where no data is available. It could be there are several reasons why there's no data available. It's some kind of shadowing effects, and especially mountainous regions, then some scattering where the beam which was reflected is not enough to put enough energy to the sensor. So it could be that there are these kind of spots in your SRTM scene. It normally depends on the processing level, that's true, but you have to deal with them and you have to correct them. And as a first step, I would like to show you how to correct these spots by using selective conditional or selective how to say it, selective mean filtering maybe. So we will fill these gaps in that file. To recalculate the elevations or to fill these gaps in the original data, we will use the raster calculator, which is a tool available in the spatial statistics toolbar. So here you can see the toolbar. If it's not visible to you, just go and customize toolbars, spatial statistics, or spatial analyst, sorry for that. You should also make sure that the needed extension for that is selected. So we will open that by clicking on that symbol for the raster calculator. You can see some a set of functions, the available layers or the available raster datasets in your project, and we will first differentiate the scene regarding data available and no data available. Therefore, we will use a conditional statement, and as you can see here, the conditional function needs two parameters. First of all, a parameter of something like a question: where is that raster layer, or where has this raster layer a value of minus 32,768, and if this is the case, what is the value the resulting raster should have? Now I've chosen the one, and I will give it a third parameter, which will say if this is not the case, it should be 0. Otherwise it would be no data. And I will also give it a name called bin.tif, and I will store it as a several or as some kind of temporarily raster. I'll press OK. It is now shown here in the results window. If this is not visible to you, just click on geoprocessing. Here are results, and it will then present you that window. And normally the resulting raster should be visible in your working area, working screen here. I have deselected that feature. I have to add that to the display itself. So now I have a binary raster. Everywhere where no data is available, it has a value of 0. If data is available, it is 1. And now I will use a second function called focal statistics, which is not available here in that function list. So we will use focal. I think it is case sensitive in that case. So focal statistics on the input raster, which is our SRTM dataset, and we will use something called number cell circle, sorry for that, number circle. And so what is focal statistics? It will compute a new raster, which is something like a result of a moving window algorithm or moving window filtering mechanism. And for that moving window, we will need some kind of information of the size and the geometry of that window. So the first information was on which raster dataset the moving window algorithm should operate, which is our SRTM data. The second information is the size and the geometry of that window. In our case, it's a circle window, and it has a radius of 10 cells, which is a unit given for that value. You can also give it a meter value or something like that. You just have to address that second parameter of the function number circle. And now we will say we would like to calculate the mean value of that window, and not the median, maximum or minimum or something like that, just the mean. And we'll close the brackets. Now everything is adjusted here, and we will store the result in a new raster set, which is called mean underscore 10. We'll also give that information of the geometry dot underscore circle dot tiff. Save it in a new file. Just press OK. Once again, it is taking some time, which leads me to introduce you to that syntax here. So this is a function called raster calculator. It is giving you something like an output raster here, a list of inputs, which is only the SRTM datasets, a list of your environmental parameters. You can adjust them by calling the raster calculator, and a message or message section where errors or something like that will be thrown in, and just by double clicking on that function name, you can recall the function and adjust the parameters, which is quite useful if you're having some kind of errors or failures in your calculations. So my calculation has finished. I will add that to the display once again. Now, well, I will adjust the color scale to the common one. There's a big hole in it, which will, we have to ask ourselves what is the value in that hole. So I will ask whether what is the value of that binary raster set in that position. I will now go to all layers, and I will once again ask for the values. Just the visibility. Click on that pixel. Now I'm in the pixel where no data was available in the original data here. The binary indicates that as a 1, and the mean value around that is 2042. And we will use the information of these 3 different layers or 3 different rasters to calculate something like a mixed raster file by using once more the raster calculator and once more the conditional statement. So we will differentiate between areas where was data available and where wasn't. So we will ask ourselves, where is the bin file the same as 1? Because there was no data available. On that pixels, we will use the information from the mean file. Else, we will use the information of the original data. We will store that information in a third one, SRTM underscore filled with means dot tiff. We'll just press OK. The session here has been cleared out. So the calculation is running, and I will add that once more to the display. The result. I'll adjust the color ramp, say in Word. Let's check whether the calculation was done correctly. Therefore, I will use the identify button. Just click somewhere, go to all layers. Now you can see that the resulting mean is at 3,245. The mean the mean around it is 3176 and the original data is 3245. So the original surface won't be changed, but it will be changed on areas where no data was available. So for the purpose of watershed delineation and hydrological analysis, we will use the calculated mean, or the calculated cleaned up SRTM dataset for our calculations. So I will now start with the total new project. I will add the last raster set to my scene. Here we are. Adjust the visibility. As I've seen, I was using the wrong parameters, so we'll use from the minimum of 1000 up to 3467. Now there's a lot more contrast available here, so we'll go into detail. And what I need now is we need to fill things. So use your toolbox, and there's a toolbox called Spatial Analyst Tools. There you have the Hydrology tab and a function called Fill. Fill will fill the things in a surface raster to remove small imperfections in the data, which is something like a built-in function as we have done prior by looking for our missing data. But it's much not coarser but finer in its calculations. So we will use our input surface raster. So it's SRTM filled means. We will go and say, well, this is a filled SRTM dot TIFF, and there's something called a Z limit, maximum elevation differences between a sink and its pour point to be filled. If the the default is to fill all sinks regardless of depth, which is quite common. So we will use that, calculate the filled DEM, digital elevation model, and here we are. So add the result to the display. No, add to display, and this is nearly the same raster set, just without the holes in it, just without things in it. So address visibility once more. As you can see, I can adjust the visibility of the layer and nothing has changed. Now what we need to do now is we have to get some information. If there's a water dropping on that surface, where is it flowing? Is it flowing northwards, southwards, or wherever? Therefore we will use a function called flow direction. The flow direction will calculate the direction of the water flow on that surface. We will use the fill SRTM dataset for that. And we will store it in something called flow direction underscore fill dot TIFF, and we will also force all edges to flow outward, which will prevent some strange behavior on the edges of a raster set. So there we go. It's not taking so long as you may suspect. And I will now add that to the display. As you can see here, this is resulting in several directions. And if you will use the help function, you will get an idea of the directions. So 4 means that this cell will flow out southwards, whereas 60 means that the cell will flow westwards. So it's quite the same as aspect calculations. which will give you an idea about the direction of the slope. So we'll now go and zoom to the whole layer. As you can see, a lot of scattering, but it's not scattering like by wrong date or something like that, but is a scattering due to the information in the file. But there's also some artifacts available. So as you can see here, there you may suggest something like a line in here, which is visible through the whole data set. This is not due to the fact that you have some kind of strange geology in the background available, but it's due to the scanning process of the SRTM in the flying direction. So we have to have a look on the results if it's still useful. So we will go with that, and we will now use a function called flow accumulation, which only needs as an input the flow direction raster. The flow accumulation raster creates a raster of accumulated flow into each cell. So each cell will then have a value representing the numbers of cells which will flow into that cell. So that is great, as you will see. We'll use the flow direction as an input. We will change the name to our flow ac_fill. So the fill SRTM was the original data for all our calculations. Output data type will be float. I think yeah, we will leave it as default, and there will be no input rate raster used for that calculations. So we will now use that, and then you should have, in the end, you should see your rivers just by the topographic and or the topography, if everything is going right. So it is taking some time, and we will, in the end of the video, we will have a look on the calculated river positions and the original river positions to see whether everything is working. So now it has finished. It was taking some time, but we will now add the resulting raster once again to the display, and we'll zoom to the layer. Here we are with our really great network of rivers. That's great. Now use the identify button to identify the values of a cell. So there are just five surrounding cells given their water to this cell. But if we will go into this one, there are more than 700,000 cells providing their input to that certain cell. What we will do now is we will have a look on that river system, or this line, which is now only a special range of numbers of pixels. So we can identify a possible river by high values of flow accumulation raster set. As there are just 3 pixels flowing into that pixel, which will probably not be enough to create a stream in the landscape, but more than 700,000 should be enough. So I've prepared a Landsat image prior to or as an input here for our project. So this is a Landsat image. Landsat data is also available on landcover.org, so just have a look on have a look there for Landsat data. Please choose the same path and row, and Here we are. So this is Central Mongolia. Maybe one or the other know Genghis Khan, which has built up its his capital for the Mongolian Empire in the 13th century in Khachurin, which is on the border of the Khangai mountain range in Central Mongolia. We'll now just adjust the band combination here. So this is Khachurin, this is the Orkhon River. It is flowing out of the mountainous region. I will now just adjust the visibility or the transparency of that layer. I will decrease it to 40% or increase it to 40% transparency. And as you can see, the whitish pixels, which are more or less representing the stream, are fitting quite well in that Landsat scene. Especially in that mountainous area, it seems to be nearly perfect. What you have to keep in mind is that the resolutions of both rasters are different from each other. So if you are looking here into our flow accumulation raster, which is which based on the SRTM data has a cell size of 90 meters, and the Landsat image has a cell size of approximately 30 meters. So there you have one uncertainty in the position of a river. Now let's go to another uncertainty. So the topography is or the changes in topography are quite significant in that mountainous area. If you're coming to the flats, you can see here there's a divergence of the real stream, which will go northwards, and the calculated stream, which is going here into northeastern directions. That depends on the cause for that is the resolution, the height resolution, or the height error maybe, of the SRTM scene, which has a vertical resolution of about 60 meters. So if you have a flat area, pixels which are near to each other can can have a different height of about 60 meters, which is quite a lot. So here the stream is now diverging from the real stream, and due to this behavior we will also suggest to have a different watershed in our calculated watersheds compared to the real watersheds. But we'll go into that detail in another video. That is it for the moment. Thank you very much for watching. If you have any comments, drop me a line. I will be pleased to see some thumbs up for my videos, and also just write me if you're coming over some kind of errors, or you have some other ideas regarding my tutorial videos. Thank you very much again. Goodbye.